kit. And at first glance, this may be a very daunting kit. Graphics itself has about 100-ish requirements for certification that map to roughly about 700 different test jobs. And these usually run across a pool of machines in a parallel fashion because certification, if you actually ran it on one machine, might take days or longer depending on the actual hardware you're trying to certify at the time. So running these tests in parallel is actually a fairly important capability. In this presentation, I'm going to talk about how these tests enable IHVs, OEMs, Microsofts, and developers to produce a really great Windows experience. And I'm going to do that in a unique way. I hope you enjoy this content. I'm going to talk about it by focusing on the scenarios and key experiences. I'll discuss the experiences from a user point of view, what the user sees, how certification test maps to that. I'll talk about reliability and scalability, what is important in that area. I'll talk about the developer experience too, which is something we usually don't think about when we think about certification. How does that actually apply to the developer experience? And then I'll also talk about the partner experience, both for the OEM and the IHV, and how the kit and the graphics kit specifically affect that. Obviously, this is a really, really broad topic. When I started planning this topic, there were all sorts of things I could have talked about. We could have gone delving into the kit itself, how you run it. We could have brought in hundreds of machines and showed you how to run a kit in parallel. What I finally decided to do was do sort of a more higher level talk that sort of orients you in terms of the kit and gives you an idea of what we were thinking, how we were thinking about the kit. And I took some notes, and actually I found that the new Samsung device is actually really nice to put notes on for your PowerPoint. I put all my notes here so I don't forget anything that I wanted to actually mention. And I'll be available in the expo room after this for questions for people who have any questions about the talk or any other topics that are related to this. So with that, let me just rephrase what I just explained in a sort of a more succinct statement. Certified WDDM graphics drivers ensure devices are designed for a great Metro-style user experience. As you saw in the keynote, every Metro application is a D3D application, either directly or indirectly. Every application is hardware accelerated. What this means is that the driver and the graphics devices are not only used more, but they're going to be used in more different ways. And so certification is more important now than it ever has been in the past. To enable these new use cases, the Windows graphics driver model has evolved and been optimized for the new experiences in Windows 8. New features have been added to the driver model to specifically address some of these scenarios. And the graphics tests in the HCK have been modified to ensure these expectations are met. The key is starting with the experience, whether it is panning back and forth on tiles, whether it's rotating the device, having that happen smoothly. It's actually testing each one of those cases. And then measuring specific things that affect that scenario and how that metric impacts the scenario. Things like memory usage, startup times, or time to first frame, other aspects. And I'll be talking about some of those things today. The certification kit is the main tool you'll use to ensure these experiences. A failure in one of these tests means that some scenario somewhere doesn't work. Now, the requirements themselves are very much written. Requirement, what's the scenario, how does it apply to graphics? The tests themselves, because there's so many, those requirements are spread out through the tests. So it may not be very obvious when you look at the test failure what scenario it affects. So you may look at a failure and say, oh, gee, that failure is not really that important. That's just some edge case. Meanwhile, when you actually map it back to the original scenario, it may be something like, well, video doesn't play in Internet Explorer. That would be a bad thing if that happened. And we've had cases like that where you look at the failure and say, why does that really happen? So we've done a lot of work to try and make sure these things map very cleanly. Now, these expectations are really important, and the expectation could be from a user point of view, whether it's failure or like performance issues like stuttering, things like that. It may be a quality issue, such as corruption of something. I'm not sure why users notice graphics corruption. You think it's just a little bit of corruption on the screen, but it's very important to people that things are fast, they're corrupt, they work correctly. There's no visual artifacts, and the system overall is stable. And lastly, I'll talk a little bit about the developer experience during this talk, and I'll talk about how these affect the APIs and the reliability of APIs, and so on. So let's talk about scenario-focused testing. When we were developing or started developing Windows 8, we took a step back and took like a broader look at how we do certification. How do the requirements get used? How do the tests get used? And we quickly realized that we had to look at certification from an end-to-end, very scenario-focused. Good graphics is really so basic. It's like air around us. We all expect it. We want it to work. We very rarely think about how graphics actually fits into the bigger scenario or the overall thing that end user is trying to complete. So to have great experiences, we want to focus our testing around the key scenarios. We started, right from the very basics, booting the system. What are the things that need to happen? How does graphics get affected there? Logging in, what happens there? How does the user log in? What requirements need to exist there? Once the user's logged in, what scenarios are going to be key? And the first things they experience, things like, really fast, performant touch response, low latency, fast animation, rotation and other things. Actually, Jensen's keynote on Tuesday showed how Metro applications would use animation to make the system really performant and so on. And so it's important that the graphics subsystem do well there. One of the things that is debuting in the Windows 8 certification kit is a set of basic performance tests around graphics and how graphics needs to function. I'll talk about these later in the deck. All right. So with that, let's move on and talk about the user experience. So the first thing that the user experience is, booting the system, whether it's booting it from a cold start or booting it from sleep or other low power states. And we stepped back and asked ourselves, what's really important here? What affects the scenario? What would you like to see? Like, clearly all of us want this to be fast, right? But we also want a number of other things. We want it to be seamless. We want to make sure there's no flicker, there's no sync lost on the monitor. And of course, at the end of the boot process, we want the user, when he's logged into the OS, we want him to be at his native resolution, which really means you should have started at native resolution in the first place to get all those things working out. Like on a mobile device, this would be the native resolution of the internal panel is what you want the system to boot to, or resume from sleep and so on. And to accomplish this, many different components have to work seamlessly together. At the very start, the firmware, either that the IHV for the graphics card needs to write, has to do a bunch of stuff. It needs to go out there and find out what is the panel connected to my machine? What's the native resolution of that? What frame buffer should I create right there in the firmware? That frame buffer then is handed off to the next stage in the boot process, the bootloader, which then uses it itself. Actually, one of the things you may not have noticed is the bootloader in Windows 8 is also high-res. It's also a graphical application. And as each step, these things go on. Now, legacy video BIOSes and things like that typically would start in 640 by 480 VGA mode. There's a good that has been around like now for 20 years. With Windows 8, those dependencies are gone. We don't actually need video BIOS. We don't need the intent system. We can actually boot the system without those. It's still there for compatibility reasons, so we can run on older hardware, but new hardware is not going to have any of that. And the new firmware on the system will actually do a lot more work to enable this seamless boot experience. Now, let's continue on. So we've handed off this frame buffer to the bootloader. The bootloader then hands that off to the kernel. As the kernel initializes, eventually at some point, the IHV's graphics driver now has started up. We can take that buffer, hand it off to IHV's graphics driver, who then takes it and continues on. And eventually the whole operating system is booted, the user can log in, and he's in native resolution. And at no point have we had to recreate the original frame buffer. At no point do we want to have sync lost on the output. We don't want that monitor flash. And we get a nice seamless high-res boot experience. And of course, the key here is that all these different components need to work very, very closely together to make that happen. So with WDDM 1.2, we enable this experience. Now, the OEM and the IHV started the firmware stage. They do the native display part of it. We in the OS have removed the dependencies on the VGA and the hardware and the vBIOS requirements. There's new DDIs in the WDDM 1.2 device driver model that the driver has to implement that let us hand off this frame buffer back and forth between the OS and the driver and various other components. Now, these new DDIs also are used in other scenarios too, like, for example, driver upgrade too, which is another case I'll mention briefly at this point. We can actually, WDDM has always been able to do a rebootless driver upgrade. This has existed in the OS since Windows Vista. With Windows 8, we can actually take the frame buffer that the driver is running at right now, hand it back to the OS, uninstall, reinstall a brand new driver, and hand the frame buffer back to the driver. At no point would we lose sync on the external monitor. The system would actually have a much more seamless experience, even on driver upgrades. Actually, one of the things you'll notice is if you ever experience a driver upgrade on Windows 8, is most people won't even notice when it happens. You're upgraded. Now, another scenario I'm going to talk about here, especially in the sleep resume case, is many applications using video memory means, or many applications using graphics means that there's much more resources using video memory. And many times, these are really large resources. They can be large textures or large objects. And when you put the system to sleep, you have to do something with those objects so that when you bring it back, it's there and you can use it. So what typically happens is you're putting the system to sleep. We look at what resources are actually used in video memory, and we have to move them to someplace safe, like system memory, so that they're available. Well, usually system memory is full because there's application data, there's applications running there. And so now we have to make room for this video memory that we're paging out into system memory for safety. And so what happens is you have to take all that content and put it to disk, which means you spin up the disk, you run a bunch of stuff, and then you move that memory around. On some of the larger graphics cards where you have gigabytes worth of memory, this can take actually a long period of time. If I have to flush a gigabyte worth of memory out to disk, just so I can make enough room to get my graphics memory out, that's a significant, tens of seconds to a minute or more. So one of the new features in WDM 1.2 that the driver implements is an optimization where the driver can tell the OS that, this memory is going to be preserved over a sleep state. You don't need to move it out of video memory. Actually, devices such as integrated devices today have that property already because their video memory is system memory. It would have been preserved anyway, so there's actually no point in us doing that sort of move of that video memory back into system memory because it already is system memory. Devices can, if they preserve their state, can tell the OS, they can mark the memory correctly, and then that sort of dance of paging memory back and forth is eliminated. Now, the key thing here is that the drivers implement this correctly and mark the various memory that they use, that it's saved or not saved. And we can optimize and make boot a lot faster. Now, the HCK provides tests so you can help validate these, but no automated sort of test that we would provide in HCK can actually catch every last thing. Has the driver marked every last piece of memory correctly? Are they doing everything that they would need to do to make this as fast as possible? So really what you need to do is actually use the tools, analyze it at every step, and make sure that everything that you could possibly do to ensure the scenario works as quickly as possible, you've done. So let's talk about another scenario, or another key scenario which we've heard a lot about, which is instant start. We want applications to be fast. We want them to suspend quickly. We want them to start quickly. In many of these cases, the application developer controls this. If they're doing the right things, they should be able to make their application fast. If they're doing the wrong things, obviously the app's going to be slower. However, there are cases where the other components, whether it's the graphics driver or other system software on the system, can affect that application and make it not possible for the developer to actually do the right things and get things done. And I'll give you sort of an example here that's maybe a little extreme. I made this one up a bit, but it sort of illustrates the point. Let's assume that there's some developer at a graphics driver is developing a feature, and they find a way of making their graphics driver like 10% faster or something. But it only costs them 60 megabytes of memory for every graphics context. And you think that's a good trade-off, at 10% faster. I just use a little bit more memory. But the point is that's 60 megabytes, and every application in Windows 8 is using D3D. Most of them will actually use more than one graphics context at a time, which means, okay, now you're using 120 megabytes per application. After you've started about 4 or 5 applications, you're up to 600 megabytes of memory being used by the system that isn't available. And as you may have heard in some of the other talks, what happens is when there's memory pressure like that, where there's a lot of memory being allocated, applications that are using a lot of memory are going to be the first ones terminated. And at that point, now you're affecting the whole overall system. What's happening is applications now have to restart rather than just resuming from suspend. So they're no longer in memory. So it slows down the user experience and affects that smooth and fast and fluid experience we want to do. So it's very important that we stay vigilant on how much memory these things are using, how quickly we can create these graphics devices in the lower levels of the graphics stack, and so on. For WDM 1.2, we've extended some of the logging and debugging capabilities. Mostly this is so you can use the tools such as GPU view and the various tools in the assessment kit to actually analyze these cases and determine how much memory is being allocated, where it's going. In the HCK itself, the performance tests we're providing are things like, how long does it take to get to the very first frame of an application? How long does it take to paint that first application? These are measured, and they're actually recorded in logs. You can actually look at each of those cases, as well as how much memory is being used. Memory is actually one of those key metrics in the graphics space that you want to constantly be looking at. As a driver developer, one of the things you want to do is make sure you're optimizing for the new Metro style experiences and applications so that you're allocating as little as possible up front, making sure you allocate as you need it and go on from there. Another scenario that's closely related to the previous one is the fast and fluid Metro style. This has been a sort of central theme of the talk so far. Again, much of this is directly in control of the application developer. However, again, the graphics driver and other components in the system can affect and play a big role in how easily the application developer can do his job. Many of the things I talked about in the previous scenario also apply here. How much memory are you using? How quickly do you create devices? How fast can the hardware move memory around between graphics memory and system memory? Those sort of things have impacts. So with WDM1.2, we have a number of features that help this experience. And they all have hardware certification kit tests to validate these. And some of these things are fairly simple, things like smooth rotation. This is mostly the driver needs to say, yeah, I support smooth rotation, and you've tested it, and make sure that smooth rotation works really nicely. There's not a lot of work. We've added some other features to WDM that are a little bit more work, but they actually also have a really big payoff. Things like the memory offer API. Sometimes, so we talked about memory pressure in the previous scenarios. The memory offer API is specifically targeting that one. What we would like to do is when applications or drivers or any other system component use memory, that they release that memory back to the system as quickly as possible. Now, the thing is, there's a tendency for people to try and keep these resources around. And the reason they want to keep it around is because you can do some sort of optimization. Let me give you an example. As an application developer, Let's say I have an application that has multiple pages, and I actually render all like 5 pages of the application. Ideally, to get a really fast experience in my application, I want to keep all those pages that were rendered around. And that way, whenever the user switches pages, I can just redraw that screen, and it's really fast. However, that screen could be big, it's causing memory pressure, it's affecting the overall system, and you don't want to do that. So with WDM1, 2, and D3D, we provide APIs where the application can say, hey, I'm going to offer this memory back to the system. And offer is interesting because what it says is, I'm not giving it away, I'm saying, you can take this if there's memory pressure and you need it. So I offer the memory. The operating system takes it. If it needs it for something else because there's memory pressure, it can take it and use that memory. If it doesn't need that memory because there isn't a lot of memory pressure, the application then can come later and say, OK, I want to reclaim that memory. And you get that memory back, that graphics resource. And actually, the content is still there because it hasn't been taken away from you. And so you get sort of the best of both worlds. If the system isn't under memory pressure, if the user's only running one application, or if you have large amounts of resources like on a desktop system, then it's available for you. So this API is available to the application developer in D3D. The same thing's available through a DDI to the driver. And drivers typically use a lot of temporary buffers, staging buffers, things that they use to talk to the graphics device, where they actually build commands and they send things down to the device. The graphics driver should do the same thing. Offer that memory back to the operating system as quickly as possible. If there's not a lot of memory pressure, that gets back. The driver can get that right back and continue on. It's fast. It's actually very fast to get that memory back. And if there's a lot of memory pressure, okay, it takes a little longer, and you might have to recreate something, but you'll still get that memory back. Okay, the last point I'm going to talk about on this slide is GPU preemption. WDM has had GPU preemption. It was introduced in Windows Vista at a DMA buffer level. These devices all use DMA level preemption. They're fast, they feel really good, they work really well. With Windows 8 and WDM1, 2, we're actually introducing new levels of preemption granularity, mid-DMA buffer and even mid-primitive level buffer. These would be hardware features that the hardware vendor would actually have to implement if they choose to implement it. And the interesting thing about GPU preemption is you can get things a little smoother. Let me give you an example. If you have an animation running, right? For that animation to actually show up correctly and smoothly, the desktop window manager needs to composite and produce a frame of the desktop every 16 milliseconds. Well, if you have an application that's doing some heavy graphical work or computation work on the GPU, with DMA level, you may miss that 16 millisecond time frame. So the experience that the user sees is either a stall in the animation or a glitch or some sort of stutter. Right? Eventually, that application will finish, will preempt, and will move and let DWM do the right thing. But with mid-level pre-MA or DMA or mid-primitive preemption, what you get is the ability to have more opportunities for DWM to get its time slice on the GPU. And that animation will then complete, DWM will come back, the application will continue, and you get, again, another smoother experience. All right. So with that, let's move on and talk about a couple other topics like stability and reliability. Did I mention that Windows 8 uses Direct3D 11 APIs by all the applications? This means that the graphics subsystem, the graphics driver, everything to do with graphics is being used a lot more by more different types of applications than ever before. And in fact, with some of the other advances that we have in Windows 8 around power management, sleep resume, standby, and so on, that system is going to be up more than ever before. People are just going to use it and use it and use it. So stability becomes more and more important. Now, the graphics driver is a very large and complex piece of software. And it's important to capture any sort of stability or reliability issues in it at an early stage before it ever gets shipped to customers and so on. So one of the things that the hardware certification kit provides is a test suite called Crash. This is a 4-hour stress run. And one of the things that you'll find is that if there are reliability and other issues, usually those show up pretty early in that 4-hour stress run. You'll be able to hit a problem, analyze it, debug it. And that means that's one less thing that a customer will actually hit in the field. Another good useful tool is Driver Verifier, which also finds all sorts of subtle sort of errors in drivers and so on. Now, other things we've done in WDDM 1.2 is we added additional features that implement some of the improved experiences. WDDM first introduced this concept of a TDR, a timeout detection recovery, which lets us detect when either the graphics driver or the graphics card itself is hung, reset it, restart, continue on. The user doesn't lose any data in their application. Things are very continue on. It's a nice experience. With WDDM 1.2, we've introduced a refinement on the TDR mechanism. And what it does is it recognizes that a GPU is actually made up of multiple engines. There's multiple components inside it. There may be a video engine, there may be a DMA engine, there may be a 3D engine inside it. And so we can actually reset a single engine. Now, so what that means is if there's an application playing video on one engine, there's an application doing 3D on another engine, and one of those issues some command or hits some bug that causes that one to have to be recovered, we don't have to reset both of them. This actually means that there's more likelihood the system seems fluid and more reliable in general. A further refinement that we've done on the TDR mechanism is occasionally, for whatever reason, an application may be doing something that always seems to hit the same bug over and over again. And you get this repeated sort of TDR behavior. It'll TDR, makes a little bit of progress, hits another TDR, makes a little progress. This actually may happen because the application is trying to be malicious and trying to do something bad in your system. One of the things that happens in the new driver model is we will actually force that application that's hitting those repeated failures to stop having to recover. We'll actually make it can't access the hardware anymore. And that application at that point falls back to software rendering. Now its impact on the overall system has been reduced. Okay, so there's a lot of things that could be done here. So again, the thing I'll point out though is the action item here is for stability, the key is just analyze failures, fix as many as you can early on. The earlier we catch those, the better it is. So, okay. Let's talk about the developer experience. I said I was going to talk about that, and it's a key theme for this talk, or for this conference, I should say. So you notice there's a theme here. I'm saying every time, Metro-style applications depend on DirectX technology and D3D11 APIs. Now, the one thing I will probably point out that some people, it may not always be clear, is that we're talking about the D3D11 API set. Application developers get a very consistent API set, so they have to write one code path. They don't have to write a lot of code paths. But the hardware underneath it may be various versions of D3D. Maybe a D3D11 device, maybe a D3D11.1 device. Could be D310 or even D3.9.3. Now, you'll have different feature sets or feature levels of hardware capability exposed to the application, but they're going to use the APIs consistently. The Windows platform, one of the things we promise our developers is that they're going to have a consistent, predictable experience using our APIs. It's going to be reliable. It's hardware accelerated, clearly. And the other thing is an application developer can develop their app on one device, and it should work everywhere. And we use certification to enable this. Another thing about developer experience that we have to keep in mind is that the usage pattern of applications is different. If any of you have been going to the gaming track, you've heard how you design a game where you allocate all your resources up front and then be as quick as possible doing your rendering loop. In other cases, you want to do it the opposite way around, where you allocate things late and so on. So you're going to see all these different usage patterns. And so it's important to look at those as well. So with WDDM, we use the certification kit to help ensure that the APIs are consistent and work correctly. In fact, the graphics tests in the certification kit use the APIs as if they were an app, the same way any other app would be. You know, they don't go around the APIs or go directly to the driver, but they use the APIs to ensure that if the certification test works, then we know that the application can count on that functionality working correctly. And we've done a lot of thinking when we actually design features in Windows 8, even at the higher levels. Stereoscopic 3D, for example, is something new in Windows 8 at the API level. So you can actually, as a D3D app, create a left and right frame. You can present it either via HDMI 1.4 out to a stereo monitor or through whatever the actual graphics card supports in terms of stereo projection. But it's the same API. You don't have to worry about, I need this API if I'm doing this. I need to use yet another API if I can't do stereo because I don't have the hardware. Because it's built into the API, it's required at the driver level. Even if the hardware can't output it, I can still manipulate my 3D stereo content, whether it's a 3D stereo picture, a 3D stereo movie, and then output it either to mono system, if that's all the system will do, or output it to stereo system, if that's what the system will do. Now, clearly, this introduces some interesting things for the hardware folks, right? Because at the chipset level, well, you're going to build the chipset so it can do stereo. Maybe in the final OEM system, you don't have stereo output for whatever reason, because you don't happen to support the right output connector or something. Or there may be other things you do at the system level where you wind up with different configurations. So in the hardware certification kit, we actually have two levels of tests. We have the device test, which tests the device. We have the system kit test, which tests the system as a whole. But the thing we'd like to see the OEMs and the IHVs and everybody else who are actually building these systems with us do is run as many of these configurations as possible. Every time there's something that could be different, where some of these tests may not, would be tweaked or used in a slightly different fashion, run those tests. Okay. And with that, we get to my last topic of today, which is going to be the partner experience. So those of you who are familiar with the certification kit, in Windows 8, you'll notice that the certification kit is very different. At a very high level, general thing, it's very different. There's a new UI. And what I'm going to talk about on this slide is some of the things that are important for the graphics part of what's new in the kit. The new UI is actually going to be a good thing for the developers. It means we can actually run that test on a developer workstation, figure out what failed. It's integrated with Visual Studio. There's a lot of really goodness for an individual developer to help us debug issues. Now, graphics in general, though, is a very massively parallel test for a submission for a logo process. And for that, there's a new object model in the kit itself that lets you as the IHV or the OEM actually implement how are you going to parallelize and distribute those tests to ensure that you get all the right combinations of things. Other new things in the kit are new concepts, new structures. Things like there's this thing called a product type. I'll talk a little bit about what product types mean for graphics on the next slide. But think about it this way. There's product types, such as a graphics card, that has a certain set of features. And to get a graphics card certified, you must have all those features, or all the ones that your device exposes if they're required to have to be there. And those features obviously clearly map to requirements, and requirements map to test jobs. And the other thing that's sort of different in the new test, or the new kit, is this thing called feature-based testing. What this means is you may have a chip, or a set of chips, or a set of systems that support various features, but they're roughly identical. As far as, for most purposes, those systems are the same. One might support some optional feature that the other one doesn't support. And what feature level testing lets us do is on every system in your pool of machines when you're doing a submission, we'll figure out what features are actually on the graphics card in that system. Those are sent back to a central controller. That controller will then issue only the tests to that system that need to be run on that system. It makes things very efficient and so on. So let's look at something more specific to graphics requirements. Now, in Windows 8, we sort of took a more comprehensive end-to-end scenario-based testing approach to certification. We wanted to be really clear about not only what needs to get done to enable this experience, but why is that experience really required? I'll give you an example. Like in Windows 8, we have an explicit requirement around what display modes a GPU must support. We're very explicit that you have to be able to support 1024 by 768 always. And this is one of those requirements that confuses people because they look at this device and say, but it's 1366 by 768. Why do I need to do 1024 on it? And the answer is actually projection and display output cloning to a second monitor. Because in most cases, the device you're projecting to, like this one, will support 1366 by 768. So I can actually clone to it a native resolution on both my tablet and also on my projector screen. But occasionally, you're going to run across a device where the only common mode winds up being the lowest one, which is 1024 by 768. And that's really sort of our safe. If you have to be able to clone, that's the one you have to support. Because if you tried to actually project and we didn't actually require that at the graphics card level, what would happen is you wouldn't be able to clone. And imagine a conference like this. You walk in with your PC, you're about to project, you connect the connector, and you can't clone, which means I can't see on the PC in front of me what I'm displaying to the audience. So now I'm trying to look over the PC, and that would be a bad thing. So we've made sure these sort of things are explicit in the requirements. We've cleaned up a lot of things about that were ambiguous or missing. And hopefully all of you will enjoy the effort that my entire team put into making sure that these things were captured. The other thing we also did was look at where we specified certain things in the requirements. We wanted to make sure that things that apply to the actual system as a whole, things like you must support the native panel resolution is a system level test because it applies to the system. It doesn't apply actually to just the GPU. The GPU is going to support all sorts of resolutions. But when you actually put the system together, you need to have the native resolution because Windows wants the native resolution. Graphics and text and content look best when the graphics being rendered in the native resolution. All right, the other thing I'm going to touch on briefly is we're actually using some of the new concepts in the new kit. We've introduced 3 new graphics products. The full graphics device is what we're all familiar with today, which is a fully accelerated graphics processor. It can do D3D, it can do display output, and can do all sorts of things. We've also introduced 2 new ones. One is a render-only device. And this is really a device that can do D3D, but doesn't have a physical display output connected to it. And this is interesting in some scenarios, such as you're going to be doing rendering on a server or something, or you're doing a compute sort of scenario. In those scenarios, this device only requires the rendering portion because it's not ever going to display out to a displayed device. And so there's no reason for that device to have to meet all the requirements associated with a full GPU. All it needs to do is pass the rendering portions. On the flip side of that, we have the other thing, which is a display-only device. This is a device that can output, but it has no rendering capability. And the place where this is, again, useful is predominantly server scenarios where you have a really big CPU. We can do all the rendering of D3D in software, but you still want to be able to see what's on the console. The system needs it. And you don't necessarily want to use the GPU all the time because you're not necessarily going to be running that sort of workload on that system. So for servers, we have this new product type called this display-only device. Now the other thing, and of course to do all this, we're leveraging the feature-based testing. We look and see what the device is, what features it exposes. So if the only features it exposes is display, those are the tests that will get assigned to that system for testing. Tests will be run, the features will be collected, a product type will be determined on submission, and you'll get a certification as a display-only device. Now, as I mentioned earlier, the graphics testing itself has introduced performance testing. Consider these sort of like a first cut of a minimum set of things we want to make sure that produce a good experience from a user point of view. These tests are actually fairly low level. They're going to be things like, like I said, how much memory is being used, how large is a device context, how long does it take to display that first frame. Over time, we're going to refine these. In future kits, we're going to improve these tests as well to, again, collect more sorts of data and so on. We've introduced a few more additional tests at the system level that are very specific around the system and things that integrate the system together. I think I mentioned one of them already was things like, what's the native resolution of the system? Does it do the 1366 by 768 if it's a tablet device? Those sort of things are tested at the system level. Now, the graphics testing also has some advanced topics. I mentioned already many times that we do parallel execution with the kit, and there's automation APIs to help you with that. There's also this thing called the device family. I sort of touched on it in a previous slide, but a device family is really a set of devices that are effectively the same, but they have certain optional features or things different between them. And what you would do is you typically take a set of devices that are in the same family, you'd put them in a pool of machines, and we will treat them as equivalent, and the right test will get executed on all those devices. And these are things that are unique to graphics testing as opposed to other devices. Other devices don't have as many tests to run and don't have to actually leverage these sort of advanced features. So with that, I get to the sort of the do these things type call to action that I'd like to ask everybody to do. Again, number one is thoroughly analyze failures. Make sure you truly understand what the root cause is of every single failure. Fix them if they're necessary, because the sooner we get them fixed and we don't have to fix them in the field, the easier it is. Run tests in more configurations, more hardware configurations, more final system configuration. Leverage the parallel execution to make things quick. And then, the other thing that's interesting is make sure that when you actually test your device, make sure that it's repeatable. Like, we've done a really thorough job to ensure that the tests, especially with feature level testing, you're going to get that repeatability with the tests. Make sure you repeat it and make sure that, don't just, like example, the crash test is one of those tests where, yeah, if you run it a dozen times, maybe you'll miss that last case where you fail. But you want to make sure you catch all of those and fix every last one of them. So with that, I'll just summarize what we've been talking about. WDM is 1.2 is the Windows 8 driver model. It's the only driver model for graphics in Windows 8 now. We provide tools in the hardware certification kit for designing Windows 8 systems. We've tried to arrange all the requirements around the scenarios so that we can work jointly to try and polish every one of those scenarios, make them as smooth as best as possible. And then look at what we have in certification and do more. Make sure you analyze every failure, fix them all, surpass the performance metrics, test more configurations than we require you to test, things like that. And invest in some of the new hardware features to make the system better and optimize. And so with that, I've listed a few related sessions. I would recommend you go to some of these. They're follow-ons to this talk or on related topics. And with that, I'll just point you to some further reading material. We do have a WDM 1.2 white paper that's posted. It will explain to you a lot of these features in more detail and how they work and so on. There's a D3D11.1 feature set document as well as DXGI 1.2 improvements. All of these links are available to you. And if there's any further question, we've created an alias on dxbuildqa@microsoft.com for email questions. Now, after this talk, I will be in the expo room at 2:30, I think it is. Please feel free to come by and we can chat. I'll be there until about 5 o'clock. Today's Thursday, isn't it? So there's Ask the Experts tonight. I'll be at the Ask the Expert as well as with all the other speakers. Please come by. We can talk about any questions you have and so on. So with that, thank you very much. Appreciate you coming.